you. All right. We start? All right. Good morning, everyone. Good morning. All right. So we framed the topic today around all the IP stuff that John mentioned, meaning, 2110 endpoints is well covered in John's presentation. What about the interconnectivity between them? How do we tie them together? That's basically the intention behind this topic today, specifically around 2110. A lot of this stuff is related to 2022-6, but specific to 2110, and we will compare and contrast what the differences are, if any. So again, starting with the simple question. Well, I have all these endpoints. I might as well just get a switch and connect them all together. And I don't know where I got this switch from. I'm surprised that Cisco has a 5-port switch, but we could connect them into this switch. So why not? What are the considerations? And guys, there's nothing prevent us from using a switch. Connect it to a switch and off you go. But there are considerations as we are specifically talking about production studios, about OB vans, interconnected sites. So what are these considerations without making it rocket science? How do you build a fabric and then get it working and then get it out of the way so that you can focus on your own production? So what we will do is we'll start with building blocks on how to attack the fabric. This will not be about, I will not cover much about IP addressing. I will not cover much about signaling. I'll touch on a bit on it, but again, from an end user perspective, you will be able, if you're a broadcaster, to talk to your IT guys and tell them what you need. And the IT guys also, hopefully, will start picking up on this lingo. So what are the requirements? So what I'm showing here is basically as we progress through building these fabrics, these IP fabrics to replace SDI routers, what are some of the requirements? So built on off-the-shelf switches, just to maintain basically the benefit economies of scale. So minimize any customization as much as you can, as much as we can. Deterministic network. When we say it's a bunch of IP stuff that is underlying carrying your traffic, you want to make sure that you don't have packet loss. You want to make sure that you're addressing the connectivity in a proper way. So we're calling that deterministic network. Endpoint synchronization. So John talked quite a bit about PTP. So again, how do we synchronize the network and what's PTP role in it? High availability, it needs to be as good as SDI router or better. That's basically our target, as good as an SDI router or better from an availability perspective. Network security. Scalability is a big issue. That's basically the question on why can't I use just a switch? Scalability. How much are you going to scale and what are the considerations there? And of course, at the end of the day, we're trying to minimize the change of the workflow to the operator. So what are the building blocks? Switches, Ethernet switches are not all the same. What I'm showing here are data center grade switches. What is unique about them? The form factor is 1RU, 2RU. And you can see they come in speeds of all the way from 1 gig, even 100 meg per port, all the way to 100 gig. And 400 gig is coming out end of this year. 400 gig ports coming out of this year from multiple vendors, not only Cisco. So again, you have this form factor, 1 gig, 1RU, 2RU. You have also the modular chassis. Okay, so that's from a form factor perspective. Why are we talking about data center grade? Data center grade because they are internally non-blocking. You see, that's key here. When we say deterministic network, for a switch at least, deterministically non-blocking, meaning any port can send to any port without packet loss. And I think there was a SMPTE presentation for people to test it actually and make sure that happens. That's indeed it. So again, not all switches are the same. These data center grade switches are capable to do that. Non-blocking internally within the chassis. Form factors, of course, you have, again, 1RU, 2RU, and the modular. The supervisors are basically the brain of the system. They come in one or dual supervisors for high availability. The 1 or 2 RUs have a single supervisor. So if the supervisor fails, that switch needs to be reloaded or replaced. The modular chassis usually has 2 supervisors for redundancy. Okay, so this is form factor. This is a building block, typical building block of a data center grade switch. You can see here the ASICs are basically where the packet forwarding is done. And that's where these types of data center grade ASICs are the ones that are able to do non-blocking internally within the switch. Again, any port to any port. The rest of it is just for management and control plane. So PTP, for example, would be running at the CPU level, but all the forwarding is done at the ASIC level. So again, we're building the building blocks for the system we're discussing. From a fabric perspective, we look at the endpoints, the 2110 endpoints, 2 types. One is native IP. So these are, what we are seeing is basically cameras. What we saw at NAB, cameras that are native IP. So produce IP out of their port. Or a common one that I'm seeing quite frequently now are playout systems. They are native 2110. So these are, again, one type. The other type are legacy endpoints, which are all across the facility. How are you going to connect them? And that's where the case of the IPGs. You hear about a lot of IPGs. That's basically what we do. This is how it looks like. And again, I'm sure all of you have seen it. On one side, it has 6 SDIs or more, and basically it translates it into 2 10 gigs. 10 gig, 40 gig, 50 gig, 100 gig, depending on the function of that IPG, IP gateway. Okay? So again, these are the endpoints that generates the 2110 signal, connects it into the fabric. So this basically will drive what kind of ports you need in the fabric. This is one data point you need, is basically what kind of ports needed into the fabric. So we have the endpoints, and we need to interconnect them. How we do that? There are 2 ways, very common right now in the industry, 2 ways. One is home run everything to a single switch. So that switch could be a 1RU, 2RU, I'm showing here a 2RU, 100 gig. 2RU, 100 gig. This is 64 ports of 100 gig. They all go into a single switch. What's the benefit of that? Space. So and of course you have modular also. So this is for like an OB van or a small studio. Everything is within a close proximity. So simplicity. Everything home runs into a single chassis. That's the benefit of it. Of course, the con is that it doesn't scale. How do you scale that? So if you run out of ports, it doesn't scale. How do you distribute it in a distributed studio facility? Home running everything doesn't scale well. And of course, single point of failure, because that system, if it goes down, your whole plant is down. Okay, so this is one way, single chassis, supported again because it's internally not blocking. You can use it. However, for again, larger scale studios, larger than an OB van, a distributed system is what we are seeing. And by distributed system, it's a class fabric. And again, this is basically a way of having a system of distributed 1RU, 2RU switches that you connect the IPGs, the endpoints to. And these are distributed through the facility. And then they connect to a couple of what we call spines, which is the aggregation point. It's the point where your signal gets distributed. Okay, so this is the fabric. Well, spine leaf, spines are basically the aggregation point, and the leaves are the top of racks that are connected. That's what we have seen. Now, this is very high level, right? And you can see we're listing sources and destinations that connects to the leaves. The benefits, of course, is close proximity to your actual production. So you don't need to home run everything. But what are the considerations? So of course, the benefit also is small failure domain. So if you lose a leaf, your remaining fabric, 90% of it is functioning. If you lose a spine, again, you have half of your bandwidth is still running. So you don't have your failure domain is smaller. But what are the considerations? The considerations are bandwidth management. That's what John was mentioning about, is ISO 6 and the bandwidth management. Because, and I'll go into the detail. So bandwidth management, network visibility. Now you have to know where the flow is going through this mesh of links, right? So again, a couple of things you need to worry about. Bandwidth management for multicast, and then visibility and maybe security also. Okay. So again, I'm describing for a spine leaf. Usually it's sporting venues, studios. We've seen it in studios. In OB van, usually they go for a single chassis because of space, again. All right, so let's discuss a major difference between, again, so this is what I get hit by the broadcast engineering team quite a bit. It's a fundamental shift in the way you think about switching. So we're talking about switching now. So your endpoint is sending, you have receivers, everything is fine. Your endpoint is trying to switch now. In an SDI router, you tell the SDI router to do that. In an IP world, it's IGMP to the endpoint. Basically, what I'm showing there is we are instructing the receiver endpoint to do the switch. So if you notice, the broadcast controller almost bypassed the fabric. All the signaling is being done using IGMP. One gentleman I worked with, he said, okay, I get it. IGMP is the gateway to the IP fabric. That's basically the way he praised it. So IGMP, what is IGMP? We'll cover it. But basically, that's a just fundamental shift, right, in the way we do it. So all this, frame sync, accurate switching, all of that needs to be thought about with this in mind, and that we are doing this switch to the endpoint, not through the SDI router, because that basically sets your expectation also from a system perspective. I will not go into a lot of details about IP addressing. Don't worry, this is not about IP addressing. But what I'm calling out here is in a unicast, when we are IPing the hosts, we care about subnetting. And again, if you know what that is, doesn't matter. In a multicast environment, there is no such thing as subnetting. It basically, our multicast will now be equivalent to flows. So the flow is basically our definition of a multicast address equal to a definition of a flow. And that's what was mentioned in the earlier presentation about tracking spreadsheets, is basically having these multicast addresses are basically representative of the flows that are in the fabric right now. But if you notice, again, there is no such thing as subnet. So again, these multicast addresses, they start from 224 to 239. That's a very large space. How does it work? So in this IP fabric, how do we do the signaling? How do we do the actual signaling of traffic? So IGMP or multicast in an IP environment is different than unicast. It's a pull mechanism, meaning the signal does not get sent until you have a receiver who's pulling the signal. So what I'm showing here are basically the receivers and the senders. So this could be an IPG, and these are some receiver IPGs. It's a pull mechanism. So the signal doesn't go through unless a receiver is hooked in and it is issuing requests to pull that traffic. And that's the, if you hear IGMP join, that's what you will start hitting if you deploy such systems, is basically, this is the IGMP message, basically pulling down the multicast traffic through the fabric. So how does it do that? How is it doing that? Basically, if I can contrast it to, so a couple of things we'll be covering in this slide on a high level. Basically, from an IP perspective, you have your protocols that you care about are the routing protocols for both unicast and multicast. This is what you will care about moving forward. These are the type of protocols you will care about. So unicast protocols are things like you hear about OSPF, ISIS, BGP. What are these? These are basically just a way for routing to distribute the reachability. So how do I reach that source? How do I reach this IP address? How do I reach that? So basically, the network distribute this information through routing protocols like OSPF and ISIS, and again. So this is what we call unicast traffic, and it will have to run in the fabric. This is basically, again, the unicast routing. It will have to run in the fabric. But this is, again, transparent to the broadcast engineering team. On top of it, there will be a protocol that handles multicast routing. So this is reachability for multicast, and this is what we care about. Because, again, all SMPTE 2110 is almost all multicast-based. OK, so the way it does it, you see, it overlays on top of the unicast is basically using IGMP from the endpoints to pull down. It basically notify the network, I need that traffic, pull it down, and then the network here, or the fabric here, will basically establish the tree, or establish the delivery to the endpoints. Okay? So again, if I leave you with anything, is that you have OSPF, ISIS, BGP. These are protocols that are running unicast. These are basically reachability of the endpoints. PIN and IGMP are the two protocols that we care about a lot, which is multicast-based. The fabric, any IP fabric, will be running this. What is the challenge with it? So I mean, we've been running this for 20, 30 years now. So what is the challenge with IGMP and PIM? The challenge with it is that it's not bandwidth aware. That's the main challenge you will see, is that it's not bandwidth aware. It doesn't know if it's uncompressed video or compressed video. It doesn't know if it's audio or metadata. So what that means is that you could end up in a system where your links are oversubscribed. That's basically, if I say one thing about 2110, is that it needs to be bandwidth aware, bandwidth aware, bandwidth aware. Your signaling needs to be bandwidth aware in the fabric, and that ties back into the deterministic network and ties back into the ISO 6. So I'm sorry, I'll take you through a couple of IGMP the way it happens is that basically, if you have a multicast stream coming into the fabric, it will stop at the fabric. It will not be pulled anywhere. We only get this stream, this 2110 stream, only if the endpoint requests it through an IGMP join. So basically, an IGMP join looks like this. I want to receive group 234.111. Easy. So it sends it to the switch, and then the network basically will use its signaling, PIM signaling, to pull the multicast stream to the endpoint. Now, one consideration here is basically, you hear about make before break or break before make. What is this all about? What is make before break or break before make? So this is basically, how do I do frame accurate switching? So if I want to do frame accurate switching in this IGMP world, how do I do that? And basically, again, these two topics of break before make or make before break. So what is it? Basically, this IGMP join, I am pulling a stream, 234.111. What if I wanted now pull a different stream and do a frame accurate switching? How do I do that? So basically, the idea is you could do it two ways. You could either issue another join, pull the stream, the new stream, and then discontinue the old stream. So that's make before break. Again, simple concept, but some concerns in the industry, well, I am oversubscribing the link, right, by a short period of time. So that's not really true, because again, you have bandwidths in these links are 10 gig and 40 gig. You are oversubscribing a 1.5 gig for a short period of time over a 40 gig link or over 10 gig link. You know, debatable whether it's doable or not, how much oversubscription. So that's make before break. Break before make is basically, no, I need to make sure that I leave no space in the link. So basically, you have to leave the stream and then join the new stream. So that's break before make. And then in that case, of course, what will happen is that you will have interruption in the picture for about 200 milliseconds, 300 milliseconds, depending on how fast your join and leave are. So most of the implementations we see are basically join before leave or make before break. But again, this is driven by the IPG. This is driven by the endpoint. This is driven mostly, that decision is driven by the endpoint. Okay, so that's a couple of things on it. Let me build the slide. Okay, so what is IGMP v3? Again, just for your awareness. So IGMP, we discussed, has been always IGMP v2. So one thing is, if you noticed in the requests, we did not specify the source of the IP address. So the source of the stream, we did not specify it. What does that mean? That means we're just saying, I need 239.111. Okay? I'm not saying where is it coming from. It's up to the network to decide where is it coming from, this 239.111. The challenge with that is that now you have to have some registry of sort where it's, it tells, the network can say, well, 239.111 is coming from this source IP address. But that's fine. It is doable. We have run it for a long time. Then there is this flavor of SSM, which again, very widely deployed right now in the IPGs that you will be dealing with, the endpoints, is IGMP v3. IGMP v3, it adds basically another point of saying, I need the group source. So I need 234.111, and it's coming from 192.168.11. Okay? So what that means is that now I know that I'm specifying the source. And guess what? Because I know the source where it's coming from, it's easier even to set up the path now. Because I know where the source is, I know the reachability. So that's the idea behind IGMP v3 versus IGMP v2. Again, these are all, without going into too much into the weed, basically these are control mechanism, signaling mechanism for the fabric to provide you with these 2110 essences, which are all, again, based on multicast. So this, okay. So now this slide is trying to show us what is the challenge with PIM. How multicast currently is not bandwidth aware. That's the main challenge. So for example, it's a busy slide, but what I'm showing here is the destination is connected to leaf 3. The source is connected to leaf 5. Okay? If I look at the destination and it's sending an IGMP join, from the view on leaf 3, the view is like this. I have 6 links, 2 each link going to each spine. So I have 6 links. Where do I pull the stream from? Right? So again, PIM is not bandwidth aware. By its nature, it's not bandwidth aware. So what will happen is that you could oversubscribe one of these links easily. And what happened? If you oversubscribe the link, this translates immediately into pixelation or audio jitterness. So basically, that's a challenge we are trying to avoid. This is part of this deterministic network that we're talking about with multicast, is how to make these decisions on how to pick which flow, which direction, make it bandwidth aware. Okay? So that's basically, that is being addressed by the concept of ISO 6. That's being addressed by the this bandwidth reservation inside the fabric. So what we covered so far is this concept of building scalable fabric that can start small, but you can scale it out. Meaning it's not a proof of concept, small lab where you have, a switch or two, that's fine. But when you're starting to build foundation for your facility, building a scalable fabric consideration is bandwidth. Again, I'm recapping what we discussed. Bandwidth management, making sure that we are able to avoid oversubscribing any of these links. Provide network visibility into the broadcast controller, meaning where is the flow going? How is it going for troubleshooting perspective? Tallies. I requested an IGMP join. The endpoint can report whether it's receiving video or not, but the network also could report that did it set up the path or did not set up the path. So that's the network visibility aspect of it. There is a security aspect of it. You want to be able to control who is connected to these leaves and prevent illegal authorization, basically. So that's the security aspect of it as well. So what we're showing there is this network controller at the top left there is basically this entity that the industry has been discussing. The idea is for that network controller to address these considerations around bandwidth management, around visibility into the fabric, and abstracting all of that into the broadcast controller. And the tie between the broadcast controller and the network controller could be, again, that's the intention behind the ISO 6 discussion. Okay? All right. So another consideration for 2110 for the fabric is the multicast scale. Why is that? In a 2022-6, we had everything in a single flow. And again, remember, the flow translates into a multicast scale, right? So you have 10,000 flows. This translates into 10,000 multicast flows. Why does that matter? Because in these data center grade switches, remember that I showed you that are non-blocking internally? These states reside inside the switch, and they have basically scale limitations. Each switch manufacturer has its own defined, how many multicast flows can I handle at one time from a control plane perspective? 10,000, 20,000? Now, what will happen with 2110 is that the same flow now will be exploded into maybe 10 flows, right? 8 for audio, 1 video, and then 1 ancillary. So what that means is that your multicast scale will explode by 10 times, from 4 to 16 times multicast scale. So that's another consideration you have to, when selecting again, consider and ask about this multicast scale, because that's a big issue with 2110 compared to 2022-6. Okay, so we talked about the multicast scale. That's another consideration. I hope that the slide is trying basically to clarify that. What other considerations do we have? Redundancy. So redundancy, again, using COD switches, not purpose-built, how do you handle redundancy? So what we have seen is basically air-gapped side A, side B deployments, where you are deploying identical fabrics on side A and side B, and you have your endpoints connected to both side A and side B, or X and Y. Okay? And you can see here it's basically fabrics with the controllers, and then the broadcast controller basically managing both sides, X and Y, where the endpoints are connected to. And this is, of course, assuming a flavor of 2022-7. So that's from a high availability perspective. All right. So we spoke about the form factor, about building the fabric, about the network controller. We spoke also about the multicast scale and high availability. Probably last consideration is PTP. So PTP is basically, there's a full session. Carl is leading it from Tektronix. So I will not talk much about PTP, except there's a lot of messages going back and forth. So a lot of messages. So what am I showing here? This is the type of messages that you expect. Sync, delay, request, delay, response. It doesn't matter. I mean, they will cover it on the next session about PTP. But just need to realize these many messages, depending on the type of deployment you have two types, transparent clock and boundary clock. So look at the number of messages that between the endpoints that reaches the grandmaster. Meaning what we're calling out here is basically all the messages from the endpoints will hit the grandmaster, all of them, and might hit the other endpoints as well. Just that's the transparent clock. Boundary clock, on the other hand, all the endpoints, look how many messages go to the grandmaster. Doesn't matter. Again, just the way boundary clock versus transparent clock is built in the fabric. So recommendation, if you have switches that are capable of doing it, do boundary clock. If you don't have such kind of switches, then you could use transparent clock. It will work, but basically you're shifting the load into the grandmaster. So let's tie it together. What I'm going to use, the AIMS reference. So this is publicly referenced document. This is basically what they published 6 months ago. If you notice, this is basically what we've been discussing today. These devices are the IPGs. And they connect basically to two fabrics. You see, leaf A, primary, and then leaf Z, primary. So they basically connect to two fabrics for high availability. And then you have a fabric that is based on leaves and spines. You notice the PTP grandmaster is connected somewhere to the fabric. Here they are showing spine. But I've seen it where it connects actually to the leaves. So the PTP grandmaster, the fabric architecture, and you see the network controller that we have been discussing, right? And the routing control system, or what we call the broadcast controller on top. So again, wrapping it together, these are basically the building blocks that we have been discussing. And then I have a couple of slides also on Ammar. I borrowed this from my colleague Shoba, and basically, again, shows you a full workflow with Ammar on top of it. And Ammar is basically, again, as John mentioned, it's for registration, it's for, so I have 2 more minutes, and then I'll wrap up. Basically, what we're showing here is, again, we discussed this fabric with a network controller. The source is registered through ISO 4. So that's for just registration. But then who's managing the endpoint? Who is basically telling the endpoint to join this source, join this group? That's basically all done by ISO 5. So ISO 5, I added ISO 5. And then ISO 6 for the management between the broadcast controller and the network controller. Okay? Do you need all of that? Today, probably not. I mean, I have seen multiple deployments I have right now without this. But this standardizes, by this I mean ISO 4, ISO 5, ISO 6. It standardizes many of the control protocols that I see today that are proprietary. That's what we like about this. So with that in mind, again, what we discussed, if I wrap it up, if you start a project, if you're starting a project today, identify the endpoints. This will help you basically to understand what are the port requirements, 10 gig, 40 gig, etc. That's number one. Size it for immediate project need, but then also how to expand. So that's basically the decision, single chassis versus multiple chassis. And then COTS switches, as you are selecting COTS switches, consider the following. Routing protocol support, so make sure, you will be surprised, make sure that support IGMP, PIM, all the routing protocols that we discussed, internally non-blocking. Again, remember we discussed these data center grade switches that are internally non-blocking, PTP support, boundary clock, hopefully, fabric architecture, if that vendor can support it, meaning bandwidth awareness, and of course high availability is basically a system design. So with that, I'm getting the signal that I have to wrap up.
Take a moment and take the opportunity while we have you here, Ammar, to take some Q&A. Even though we're running a little late, I think we'd all benefit from that. You may not be able to be here for the
perfect
Q&A in the afternoon after
sure.
the super session's over.
Yes.
I appreciate the redundancy of spine and leaf network. If you have Check here. There we go. If in a spine and leaf network, if you have a device that has basically dropped connectivity on one connection to a leaf, is at some point is there a comparison between what one side knows and the other side knows to see, because you've lost in essence the support of the redundancy, but you may not know it because your traffic is still getting from the device to the controller. At some point, is there a comparison of the directories so that you can say, one side of the fabric can see this, but the other side cannot?
Got it. So the question here, you have a failure here between, let's say, this source, two links, one is failed, and how do I notify that? Because the traffic is still going, right, on one side. So how do we do that? So there are 3 ways of doing it. One is remember, on the endpoint. The endpoint can signal to their broadcast controller. So the endpoint is signaling to the broadcast controller without a doubt. They will say, I stopped receiving on one side, and I've seen that. That's number one. From a network perspective, this is where the ISO 6 comes in play. Because current, and ISO 6 is standardization of current process. So currently, this controller here, currently we have it reports to broadcast controller if a link is down. And if you noticed here, at least this is the Cisco architecture that we are deploying. We have 2 controllers, one per side. And you can see they are both talking to the broadcast controller on top. So basically the idea is the broadcast controller will be notified by one of these controllers that a link is down also. So there are 2 ways of keeping it. And I think it's a good idea to keep it separate. Meaning you have this path and you have this path, just like the tallies. The tallies, same thing. So a tally could be that a destination will notify the broadcast controller, hey, I'm receiving the signal, and also the broadcast controller will get notification from the fabric itself, and it can cross-reference the same thing.
I'm just thinking about what I know about networking, which is still not as much as I'm going to need. But the idea of the network controller in a typical IP network, you don't need a network controller because all the protocols make sure that everything communicates with each other. So this is this specifically for an environment where we're trying to do things like 2110?
Very good call. Do I need a network controller? This network controller, is this used in traditional facility? So to answer is yes and no. Yes and no. Why? So why? What the gentleman called is basically IP is distributed by itself. All the control protocols that we discussed are distributed by nature. We've been doing this for 20 years. It's distributed. That's how it started. So each of these has its own control protocol. Do I need a controller? In general, in the IT world, there is some notion that has been running for about 6 years now of having a controller. And that controller could achieve different functions. In our world, we're saying this is, to your point, is it absolutely necessary? No, I have many facilities that are running without this controller. What this controller is doing is some of the deployments are saying, look, I need abstraction because I don't want to train my staffs on troubleshooting multicast. So what do? Get a controller, and then it does the abstraction, it does the visibility. Bandwidth management, same thing. You could do it in the fabric without needing a network controller. Correct, same thing. So it's honestly, when we see the network controller, 2 things. There's a trend in the industry of introducing a controller of sort for automation. That's in general in the industry, like in the IP industry. And the other is some of these, again, abstraction, and while the broadcast engineering are picking up the speed, these are some of the functions that the network controller can do. So that's basically what we are noticing. Go ahead.
Yeah, it seems like both of your question, your answer kind of touched on training and education. One of the things I was told when I first heard convergence in NAB a million years ago was you cannot use traditional IT strategy in a media-aware IP network. So what would be the training? You said, you said about not training, teams on multicast. So what would someone like me and the gentleman up here, how would we learn? What would we go? What class would we take to start to get up to speed on this?
So good question. So let me start by the training. So for example, training, Cisco, maybe other vendors will do the same thing. Cisco is offering in June media-specific track, like similar to CCNA, but it's for media. And it basically touches to a lot of these things, PTP, and again, remember, the other second answer is that this is all based on off-the-shelf switches, nothing purpose-built. These are the exact same switches that Goldman Sachs is running their financial network on. This is exact same switches. No, maybe like a couple of features in software. So definitely this is what IT is running, same thing. But when by IT, I mean, again, Goldman Sachs and the financials of the world. Training-wise, Cisco is releasing, again, in June timeframe, this media-focused CCI. And what allows you to do is certification also. So basically, certification also. Many of this is traditional multicast. But there are some flavors around PTP, around this bandwidth awareness, that will be introduced in June. And I'm sure other vendors will do the same thing. I hope to, the switching vendors.
No, is the training in June, or are they going to announce it in June?
The training is starting in June. So we had a couple of beta classes in November, December timeframe. We had many attending it from both the VARs as well as the customer base, and they are gonna release it in June. It's basically cisco.com, go media, keep an eye there, because again, so cisco.com//go/media, it will be posted there as far as training. We hear that all the time.
Okay, no, I'm going to
Perfect.
back too late. That was great, Ammar. And
Thanks.
matter of fact, those last questions, as I was just saying with Carl, is a good segue into Carl's IP Roadshow introduction. It's only going to be a short 10-minute intro to